Welcome back, everybody. So now we're going to look at bases other than e. We focused on the natural logarithm and base e exponential functions. Now we're going to look at other bases. So base 2, base 4, base 6, base pi, whatever base value that we run into. So just by way of review, we'll review a little bit on solving exponential equations. So there's a whole host of different ways you can approach them. So we could take logarithms of both sides. We can rewrite our powers in different values. Lots of different ways we can approach them. So I would just say for the homeworks, make sure to kind of review a little bit on your approaches to solving these. So if we look at number 1, we have 4 to the x is equal to 1 over 64. This one is so simple, we could just guess a value if we wanted to. We can kind of see what the answer is going to be. But some approaches we might try would be to rewrite both sides as the same base. So if this is 4 to the x, then 1 over 64 perhaps could be written as a really nice 4 to a power value, and we can see that that's going to be 4 to the negative third. And if we have the same base and they're equal to each other and the values of the numbers are equal to each other, then the exponents have to be the same as well. So we could just say x equals negative 3. If we wanted to be more complicated, we could say log base 4 of 4 is equal to the log base 4 of 1 over 64. Sorry, 4 to the x. And then we could bring down the x using the power property, and then just evaluate each one of these logarithms. So log base 4 of 4 is just 1. And then log base 4 of 1 over 64, as we saw a moment ago, would be negative 3. So x would equal negative 3. So there's a whole bunch of different ways you could choose to kind of approach each equation that you're solving for. So use the proper tools accordingly in a way that's going to be simplest for you. For number 2, we've got a log equation that we want to solve. And so this also has a number of different approaches, but the main approach that you're going to have to use in this case is going to be either to rewrite 3 as a logarithm base 2, or to rewrite this using an exponential form. So let's say we wanted to rewrite this using an exponential form. We could combine these two logarithms on the left by the product property since we're adding. So this would become log base 2 of x times x plus 2 is equal to 3. And then we could rewrite this by taking the power of 2 on both sides and treating these as exponents. So in other words, 2 to the log base 2 of x times x plus 2 is equal to 2 to the third. Or you could rewrite it as 2 to the third equals that value, which would be kind of an equivalent type of expression. So let's say that we raise both sides as exponents base 2. So we're going to get x squared plus 2x if we distribute the product inside there as 2 to the third, which is 8. So then x squared plus 2x minus 8 is equal to 0. And now we've got a quadratic. So that looks like it's going to be x minus 2 times x plus 4. Let's see. Yep, I think that works. So x is equal to 2 and negative 4. However, with log equations, we do have to be careful about these domain values. So this cannot be negative. It has to be greater than 0, which means we have to throw out negative 4 as a possible answer. So the only answer would be x equals 2. Now again, the other approach would be to rewrite this as log base 2. We could still combine with the product property, but on the right-hand side, instead of 3, we could rewrite that as log base 2 of 8, since 2 to the third is equal to 8. And then we end up with the exact same equation that we got in the previous form, and we could work it out the same way as well. So getting logarithms on both sides by introducing a number as a logarithm. So any number can be written as a logarithm of any base. Or using this exponentiation inverse property, it would be perfectly fine as well. So again, just make sure that you feel comfortable with whichever method you're going to be using. And again, those logarithm properties are listed below there. of ones that are going to be the most common that we use. Now what we're going to do for logarithms that are not base e is we're going to make them base e. So this is going to be the key idea. Because the natural logarithm has such a nice derivative, we want everything to be in the natural logarithm essentially. So any log base value of x that is not base e, we're going to use the change of base property. So note this is just using the change of base property for logarithms. So log of the power value over log of the previous base is going to be how the expression looks. And we're going to rewrite it as base e. Note a is going to be a positive number for our bases. And again, all this is going to mean is that we get 1 over the natural log of a, some number, times the natural log of x. So we're going to think of that natural log of a as just a coefficient, 1 over natural log of a, as the coefficient being multiplied to our natural log of x expression. Okay. So using that then as a definition, we can get some nice properties for our derivatives that'll be pretty simple to use. So let's start with the logarithm itself. So if we want to take the derivative of this function, again, we'll start by rewriting it as 1 over the natural log of a times the natural log of x. And then we can directly rewrite this just differentiating directly. So we'll get 1 over the natural log of a times, of course, the derivative of the natural log of x, which is just 1 over x. So that means that the derivative of any log value is going to be 1 over the natural log of a times x. And clearly we can see if we let a be e, then we would just get 1 over x, the normal derivative value that we end up with. Okay. And then for exponential equations, so if we have y equals a to the x, we can't just rewrite it as a base e expression because we don't have any logarithms, but we can use log differentiation the way that we did earlier. So if we take the natural log of both sides, we'll get the natural log of y is equal to x times the natural log of a. And now we can differentiate implicitly with respect to x, like we did improving e to the x. So we'll get y prime divided by y, or 1 over y times y prime. Maybe we should write it that way. So 1 over y times y prime is equal to x times the natural log of a is just going to be the natural log of a. And then y prime is going to equal the natural log of a. We can multiply both sides by y. So we'll get natural log of a times y, which from our initial starting point is just a to the x. So the derivative of a to the x is just natural log of a times a to the x. In other words, if we have base e, obviously that's going to be 1. And so this is really just some constant of proportionality, which in this case is exactly the natural log of our base. So that's really kind of nice. So natural log of a times a to the x. Okay. Chain rule then is going to be very similar. So for the chain rule, so we're going to use what we just derived below here. So we're going to definitely get the natural log of a times a to the u, and then we'll just multiply that by u prime. And then for our log base a of u, again from above was 1 over the natural log of a times x. That is going to look like 1 over the natural log of a times u prime, which we can then just put as a single expression, u prime over natural log of a times u. And for these, once you're getting used to them, I would definitely practice a bit, maybe just using the log properties the way we derive them here. But as you use them more, you'll just get used to rewriting them in that way. All right, so let's go ahead and look at a few examples. So we have y is equal to 3 to the x. So again, if we wanted to, we could take the natural log of y and the natural log of 3 to the x. and then rewrite this as the natural log of y is equal to x natural log of 3, and then just differentiate both sides. And then y prime would equal natural log of 3 times y, which is going to be the natural log of 3 times 3 to the x. But note, we could have gotten that directly from the rule that we worked out above. So it'll be the natural log of our base times our exponential expression. Okay. For number 2, now we're going to take the derivative of the logarithm. And again, you could rewrite this as the natural log of x squared plus 2x over the natural log of 4. So you could use the change of base property, and then you just would be differentiating the top portion, which y prime is just going to be, so we've got 1 over ln of 4. We can just leave that on the outside, and then the derivative is going to be 1 over x squared plus 2x times the derivative of x squared plus 2x, which will be 2x plus 2, and that will be our derivative. But you could also have just written this as the derivative of u. Oops. So similar to what we had up here. The derivative of u over the natural log of a times u, which is exactly what we have here. So we could just go directly to 2x plus 2 over the natural log of 4 times x squared plus 2x. But again, feel free to just use that, either the log differentiation we did for number 1 or the change of base property we did for number 2 to start, because there's no wrong way to do it as long as it's correct. And then for f of x equals 5 to the sine x, f prime of x then, if we're using that property for differentiating exponentials, we'll get the natural log of 5 times the derivative of sine times our original function. So that would just be doing it directly as opposed to taking the log of both sides. Okay. So then if we scroll down here, we've got integration. So how do we integrate exponential functions? So if we remember a to the x, just above here, that's natural log of a times a to the x. Then if we go in reverse, what would that be? So maybe we could do a couple more here. So let's say we took the derivative with respect to x of that derivative expression, right? So natural log of a is just a coefficient, so we would take the derivative of a to the x again, and we'd get natural log of a squared a to the x, because now there would be 2 of them. And if we took the derivative again, we would then get the natural log of a cubed times a to the x. So if we're differentiating downward, we're just going to be multiplying by the natural log of a each time, which means if we go in reverse, we're dividing by the natural log of a. So what we'll end up with is a to the x over the natural log of a plus c. All right, so then for our examples below then, if we want to, we could do a u substitution, right? A really simple one, but we actually don't need to because it's so simple. But if you wanted to do a u substitution, you'll definitely be doing u substitutions with these. So this is going to equal 2 to the sine x over the natural log of 2 plus c. Again, just using that form above. And then for 2, we'll get 3 to the x over the natural log of 3, evaluated from 0 to 2. So we'll get 9 over the natural log of 3 minus 1 over the natural log of 3, which is going to simplify to 8 over the natural log of 3. All right. So two quick notes here are going to be definitions for E. These definitions we're actually going to prove, but we're not going to prove them quite yet. So they require a little bit of work to work them out. So we'll definitely work out these limits later on, but these are two limits that you might see. The most familiar one is going to be this compound interest version, where it's 1 plus 1 over x to the x. But there are various ways that we can write these different limits. And for applications then, we've got a bacteria problem as well as some compound interest problems. So these are all kind of review type of examples. So I'll let you work these ones out on your own. You are going to be using the derivative and integral properties, but I think we'll save these for the next video. So if you have any questions, definitely shoot me an email or come by the office hours. Otherwise, until I see you next time, take care.